Maine, January 1907. The thermometer read 20 degrees below zero. In the depths of the North Woods, where white pines stood 200 feet tall and snow buried the forest floor under 6 feet of powder, winter had always meant one thing: shutdown. Horses froze in their traces. Men lost fingers to frostbite. Ice roads cracked under impossible loads. The timber stayed where it fell, locked in place until spring thaw made the rivers run again. But on this morning, something moved through the blizzard that defied every rule the loggers knew. 20 tons of riveted steel and cast iron, steam hissing from brass valves, twin crawlers chewing through drifts like they were nothing. Behind it, a train of sleds carrying 300 tons of prime timber, more wood than 60 horses could drag on their best day. They called it the Lombard Steam Log Hauler. The men who first saw the blueprints called it suicide on skis. The bankers called it a waste of money. The horses, if they could speak, might have called it salvation. This is the story of the machine that turned winter from enemy into opportunity. The iron beast that proved you didn't need roads, didn't need spring, didn't even need wheels, if you understood steam, weight distribution, and the physics of frozen ground. Before we drag you into the snow and steel, hit that subscribe button and drop a comment telling us where you're watching from. We got iron beasts from every corner of America, and we want to bring you the machines that built your region. Now, let's see how 20 tons of steam conquered the coldest frontier in American industry. Before the Lombard, winter logging wasn't just difficult. It was a calculated gamble with lives, money, and time, and the house always won. The timber had to come out. That was non-negotiable. America's cities were growing faster than anyone had predicted. Railroads needed ties. Mills needed raw logs. Construction needed boards. And the best timber, the straightest pine, the hardest oak, grew in places where winter turned the land into a white hell for 6 months every year. So the logging camps tried. They used what they had: horses, sleds, and ice roads. Crews would spend weeks preparing a route, packing snow, flooding it with water hauled in barrels, letting it freeze into a glassy surface. When conditions were perfect, a team of 6 to 8 draft horses could drag a sled loaded with 8 to 10 tons of logs, maybe 12 tons if the ice held and the grade wasn't steep. But perfect conditions were rare. Temperatures swung wildly. A warm day softened the road. A cold snap made it brittle. Horses broke through. Sleds tipped. Loads scattered across frozen lakes. The animals suffered worst of all. Working in sub-zero cold, breathing hard, sweating under harnesses. Pneumonia killed them by the dozens. Frostbite took their ears and hooves. A single winter season could burn through 30 horses in a medium-sized camp. The men didn't fare much better. Teamsters worked 16-hour days in temperatures that froze spit before it hit the ground. One mistake, a snapped chain, a spooked horse, a sled running wild downhill, and you were crushed or worse, dragged. Camp records from the 1890s show injury rates that would shut down any modern operation in a week. And even when everything went right, the math didn't work. A good horse team could make 2, maybe 3 trips per day, covering 8 to 10 miles round trip. That meant 20 to 30 tons of timber extracted per day, per team, if weather cooperated. For a camp trying to harvest thousands of acres before spring, it was nowhere near enough. The economic pressure was crushing. Timber companies had purchased vast tracts of forest land on credit, betting they could extract and sell wood fast enough to cover their loans. But winter, the only season when the ground was frozen solid enough to support heavy loads, gave him a narrow 4-month window. Miss that window, and the log sat until next year. Default on the loan, and you lost everything. Camp operators pushed harder, bought more horses, hired more men, extended the work days. It didn't matter. The bottleneck wasn't effort. It was physics. Horses could only pull so much. Ice roads could only handle so much weight. And when either one failed, people died. There were whispers of alternatives. Steam traction engines had been tried in summer logging operations out west, dragging loads on dirt roads with mixed success. But wheels were useless in snow. A few inventors had patented track designs on paper, but nobody had built one that worked reliably under real field conditions. The technology existed in fragments. Steam power here, continuous tracks there, but no one had put them together in a machine tough enough to survive a Maine winter. The logging industry was stuck, burning through men and animals to move timber at a pace that barely kept the mills running. Winter logging was an industry. It was a war of attrition. And by 1900, the loggers were losing. Alvin Orlando Lombard wasn't a logger. He was a tinkerer, a mechanic, and a man who couldn't let a problem sit unsolved. Born in Springfield, Maine, in 1856, he'd spent his life around steam engines, water wheels, and the kind of practical machinery that ran sawmills and gristmills across New England. He understood power. He understood mechanics. And when he looked at winter logging, he saw a problem that steam could solve. If you rebuilt the machine from the ground up, the trouble with steam traction engines, the big, wheeled monsters farmers used to pull plows and thresh grain, was simple: wheels. In mud, they sank. In snow, they were useless. Lombard had watched crews try to adapt them for winter work, bolting on wider rims, adding chains for traction. Nothing worked. The engines either bogged down in the first drift or spun their wheels uselessly on ice. So Lombard did what no one else had seriously attempted. He kept the steam engine, the boiler, the firebox, the cylinders, and throughout the wheels, in their place. He mounted a pair of continuous track assemblies, heavy wooden slats faced with steel cleats, running on drums driven directly by the engine's power shaft. The weight of the machine was distributed across 10 feet of surface contact, instead of 4 small wheel patches. It was the same principle loggers used when they strapped wide snowshoes to their boots. Physics didn't care whether you weighed 180 pounds or 20 tons. For steering, Lombard added a pair of massive wooden skis at the front, 8 feet long and a foot wide, controlled by a chain and lever system. The operator sat exposed on a platform above the boiler, lever in one hand, throttle in the other, watching the snow ahead and the sled train behind. He built the first prototype in 1899 in a small shop in Waterville, Maine, using scrap parts, salvage boilers, and whatever steel he could afford. When he rolled out for the first test, the logging bosses came to watch. They stood in the snow, arms crossed, shaking their heads. Too heavy, too complex. It'll break the first time it hits a stump. The boiler will freeze. The tracks will tear off. Lombard fired up the engine, let the pressure build to 125 pounds per square inch, and drove it straight into a snowdrift 4 feet deep. The crawlers bit. The machine moved. The crowd got quiet. But moving through a snowdrift wasn't the same as hauling timber. Lombard knew that. So did the logging bosses. The real test came 2 weeks later, on a frozen lake outside Waterville. Lombard loaded 3 sled behind the machine, 40 tons of oak logs chained together in a train. The ice road crew had prepared the surface, flooding and freezing it smooth. Conditions were perfect. If the machine was going to fail, this wasn't the place. But if it succeeded here, it proved nothing about working in rough country, in blizzards, on grades where ice roads cracked and sleds jackknifed. Lombard opened the throttle. The engine chugged. The tracks began to turn, slow at first, then steady. The chains went taut. The sleds lurched forward, and the Lombard pulled. Not fast, maybe 2 miles per hour, walking speed, but it pulled. 40 tons of dead weight, gliding across the ice behind 20 tons of steam and steel. The machine didn't slip. It didn't stall. It didn't sink. It just worked. By the time Lombard circled the lake and brought the train back to the starting point, half the crowd was already talking about placing orders. By 1901, Phoenix Manufacturing Company in Eau Claire, Wisconsin, had licensed Lombard's design and started production. The first commercial units rolled into Maine logging camps that winter. The age of the iron snow beast had begun. The Lombard steam log hauler wasn't elegant. It was a brutal assembly of steam power, steel, and mechanical advantage, designed to do one thing: move impossibly heavy loads across terrain that would stop anything else dead. The core was a vertical fire tube boiler, riveted steel, standing about 6 feet tall, wrapped in sheet metal and minimal insulation. Inside, a firebox burned cordwood or coal, heating water to generate steam at working pressures between 125 and 150 pounds per square inch. That steam fed into a twin-cylinder engine mounted horizontally just behind the boiler. Each cylinder had a bore of roughly 8 inches and a stroke of 10 inches. When steam expanded in those cylinders, it drove pistons connected to a crankshaft, which turned a drive shaft running to the rear track assemblies. The tracks themselves were the innovation that made everything else possible. Each crawler consisted of a series of wooden slats, typically oak or ash, about 3 feet wide and 6 inches thick, connected by heavy steel pins and rollers. The outer face of each slat was fitted with steel cleats, triangular teeth that bit into snow and ice. The tracks ran on large drums at the rear, driven by the engine, and on smaller idler wheels at the front. The entire track assembly measured roughly 10 feet long, giving the machine a footprint that distributed its 20-ton weight over an area equivalent to a dozen horses standing side by side. This wasn't just about not sinking. It was about traction. The cleats dug into the surface with each rotation, gripping ice and frozen ground in a way smooth wheels never could. In soft snow, the machine pressed down just enough to pack a firm path, then climbed over its own compressed track. On hard ice, the cleats fractured the surface, creating micro-anchors that prevented slipping even on a 5 or 6 degree grade. At the front, the steering system used a pair of massive wooden skis, each about 8 feet long, a foot wide and shod with steel runners. These weren't passive guides. They were load-bearing structures that carried the front third of the machine's weight. A chain and lever mechanism connected to the operator's station allowed the skis to pivot left or right, carving into the snow to change direction. The skis alone weighed several hundred pounds each and had to be replaced periodically as the runners wore down or splintered from hitting buried obstacles. The operator sat on an open platform directly above the boiler, in full view of the snow ahead and the sled train behind. Controls were simple: a throttle lever to regulate steam flow to the cylinders, a brake lever connected to friction bands on the drive drums and the steering chain. A steam whistle, operated by a pull cord, allowed communication with the crew on the sleds. Gauges showed boiler pressure and water level, critical numbers, because if the water dropped too low with the firebox still roaring, the boiler could rupture. Drawbar pull, the measure of how much weight the machine could drag behind it, ranged from 8,000 to 12,000 pounds of continuous pulling force, depending on surface conditions and engine tune. That doesn't sound like much compared to the 200 or 300 tons of logs a Lombard hauled. But the trick was in the sleds. Logs were loaded onto multiple sleds in a train, connected by chains. On a properly prepared ice road, the sleds glided with minimal friction, maybe 50 to 80 pounds of resistance per ton of load. So 10,000 pounds of pull could move 250,000 pounds of timber, as long as the ice held and the grade didn't steepen past the machine's climbing limit. Weight, pressure, traction, and mechanical advantage. No computers, no sensors. Just steam, steel, and men who understood exactly how much force a machine could deliver before something gave way. Fuel efficiency, or the lack of it, was a known trade-off. The Lombard consumed cordwood at a ferocious rate, roughly 300 to 400 pounds per hour under load. That meant a full day's operation required between 2 and 3 cords of split, seasoned wood, usually hauled to the work site the day before. Coal could be used and burned hotter, generating more steam per pound, but it was expensive to transport into remote camps and required different firebox management. Most operators stuck with wood. It was everywhere. It was free if you cut it yourself, and the firemen already knew how to manage a wood fire. Thermal management in sub-zero conditions was its own challenge. The boiler radiated heat constantly, which kept the operator warm but also wasted energy. In extreme cold, 20 or 30 degrees below zero, heat loss accelerated. The water in the boiler cooled faster, requiring more fuel to maintain pressure. Worse, any exposed metal parts, the drive shaft, the steering chains, the track pins, contracted and became brittle. Operators learned to keep a can of heavy grease near the firebox, warming it just enough to stay liquid, then applying it to critical joints before each shift. It was crude, but it worked. A well-maintained Lombard could operate reliably down to 40 below, as long as the fireman kept the pressure steady, and the engineer didn't push the machine past its mechanical limits. If you're hooked on this kind of practical, no-nonsense engineering, smash that like button and subscribe. We're taking you deeper into how these crews kept the Iron Beast running in conditions that would freeze a modern diesel solid. Keep watching. Operating a Lombard wasn't a job. It was a partnership between man and machine, played out in sub-zero cold, where one mistake could kill you and hesitation could strand 20 tons of iron in snow too deep to dig out. The day started hours before dawn. The firemen arrived first, usually around 4 a.m., carrying an oil lantern and a splitting maul. His job, get the fire going. In January, in the Maine woods, the water in the boiler could freeze overnight despite the residual heat from the previous day. So he'd check the water level first, sometimes having to crack a skin of ice on the gauge glass. If the level was safe, he'd load the firebox with kindling and cordwood, coax a flame to life, and begin the slow process of building pressure. If the level was low, and the water had frozen in the supply lines, he'd have to haul buckets from a nearby stream, chipping through ice a foot thick to reach liquid water below. By the time the engineer arrived, usually an hour later, the pressure gauge should be climbing past 100 psi. The engineer was a senior man, the one who'd trained on stationary steam engines in sawmills or on locomotives before transitioning to the woods. He'd inspect the tracks, checking for broken cleats, loose pins, or cracks in the wooden slats. He'd test the steering chains, grease the drive shaft bearings with whatever heavy oil hadn't frozen solid, and make sure the brake bands weren't stuck. Only when he was satisfied, and the boiler pressure had stabilized around 125 psi, would he signal the firemen to keep feeding the fire. Starting the Lombard was a ritual. The engineer would crack the throttle, just a quarter turn, letting steam into the cylinders. The pistons would move, slowly at first, almost reluctantly, fighting the cold and the stiffness in every joint and bearing. The drive drums would rotate. The tracks would start to crawl forward. If everything sounded right, no grinding, no slipping, no hiss of steam escaping from a failed gasket, he'd advance the throttle and guide the machine forward into the timber yard where the day's load was waiting. Communication was done by whistle codes. 1 short blast, stop. 2 short blasts, forward. 3, reverse. A long, sustained blast, emergency. The codes had to be simple and loud, because the noise from the engine, the rhythmic chuff-chuff-chuff of the pistons, the clatter of the tracks, the roar of the firebox, drowned out any attempt at shouting. The brakeman, riding on the last sled in the train, would signal back with a hand wave or, if visibility was poor, by tugging on a bell rope strung along the length of the sled train. Fueling the beast was constant work. A Lombard running at moderate load consumed between 300 and 400 pounds of cordwood per hour. That meant the firemen never stopped moving, splitting wood, feeding the firebox, watching the steam pressure, adjusting the dampers. If the pressure dropped below 100 psi, the machine lost power and could stall in deep snow. If it climbed above 150 psi, the safety valve would blow, wasting steam and announcing to everyone within a mile that you didn't know your job. Water was just as critical. The boiler held roughly 200 gallons, but at full load, the engine consumed water fast. Crews carried spare water in barrels strapped to sleds, refilling the boiler through a hand pump whenever they stopped to adjust chains or reposition a load. In extreme cold, the pump itself could freeze, forcing the fireman to thaw it with direct heat from a firebox or, in desperate moments, his own body warmth. Maintenance happened in the field with the tools they had. A broken track cleat? Pull the sled train off to the side. Use a sledgehammer and drift pin to knock out the damaged cleat. Bolt on a spare if you had one. Or improvise a wooden block if you didn't. A stuck valve? Shut down the engine. Let the pressure bleed off. Disassemble the valve housing with a pipe wrench. Clean out the carbon buildup, reassemble, and restart. A frozen steering chain? Heat it with a torch improvised from a kerosene-soaked rag wrapped around a stick. There were no repair shops in the woods. No replacement parts shipped overnight. If the machine broke, you fix it where it sat, or you lost a day, and possibly the week. Coordination between crew members was a dance learned through repetition and necessity. The engineer couldn't see what was happening behind him. The sled train stretched 50 to 100 feet back, often disappearing into blowing snow or around curves in the trail. He relied entirely on the brakeman's signals and his own sense of the machine's behavior. If the load suddenly felt lighter, If the resistance dropped, it meant a chain had broken or a sled had tipped. He'd hear it in the engine's rhythm, feel it in the throttle response. Experienced engineers could diagnose problems by sound alone. A grinding noise meant a track cleat was damaged. A hiss meant a steam leak. A high-pitched squeal meant the brake bands were dragging. The psychological toll of working on a Lombard in winter was rarely discussed, but it was real. The engineers sat exposed on an open platform for 10, 12, sometimes 14 hours straight, surrounded by noise and heat, but staring into a landscape of white and cold. Frostbite was a constant threat. So was carbon monoxide from the firebox, especially in still air when the wind wasn't carrying the smoke away. Men reported hallucinations after long shifts, seeing trees move that weren't there, hearing voices in the whistle blast, feeling the machine lurch when it was standing still. The camps rotated crews when they could, but in peak season, there were never enough trained operators. Some engineers worked 6 days a week, every week, from December through March. The pay was good, 3 or 4 times what a teamster made, but the job aged men fast. The rhythm of the work was hypnotic and unforgiving. The engineer sat on his platform, eyes scanning the trail ahead, one hand on the throttle, the other ready to steer. The fireman worked behind him, sweat freezing on his face despite the 120-degree heat radiating from the boiler. The brakeman rode in the rear, watching for chain failures, shifting loads, ready to leap clear if a sled tipped. And the machine itself, 20 tons of iron and steam, churned forward through snow and cold, indifferent to human comfort, responsive only to the physics of heat, pressure, and traction. It was brutal. It was dangerous. And it worked. Operating a Lombard steam log hauler wasn't just difficult. It was a continuous negotiation with forces that could kill you in seconds. Cold that stopped your heart, ice that gave way under 20 tons of iron, and mechanical systems that didn't forgive mistakes. The cold was the first enemy. Temperatures in the north would routinely hit 20 below 0 Fahrenheit, and during deep winter cold snaps, they'd plunge to 40 below or worse. At those temperatures, metal became brittle. Steel that was flexible at room temperature could snap like glass under shock load. Track pins that normally flexed and absorbed stress would fracture if the machine hit a buried stump too hard. Operators learned to avoid sudden starts and stops in extreme cold, easing the throttle open gradually, letting the metal warm up through friction and the radiated heat from the boiler before demanding full power. But cold killed in subtler ways, too. Frostbite could claim fingers in minutes if you weren't wearing heavy mittens, and mittens made it nearly impossible to work the fine controls or handle tools during repairs. Men learned to work in cycles. 2 minutes of exposed handwork, then thrust your hands into your armpits or near the firebox to restore circulation. The engineer, sitting on an exposed platform with wind rushing past at 5 miles per hour, faced constant exposure. Period reports describe cases of severe frostbite on ears, noses, and cheeks. Tissue damage that took weeks to heal and often left permanent scarring. Some operators wrapped wool scarves around their faces, leaving only a narrow slit for vision, but that limited awareness and made it harder to hear the machine's warnings. Ice roads were the second enemy, and they were treacherous. The entire winter logging system depended on a smooth, solid ice surface to reduce friction and allow heavy loads to glide. Crews would spend days preparing a route, packing down snow with horse-drawn rollers, then flooding the packed surface with water hauled in barrels or pumped from nearby streams. When it froze, ideally in layers, built up over several nights, it created a road surface harder than pavement and slicker than glass. Under perfect conditions, a sled loaded with 10 tons of logs had a friction coefficient low enough that the Lombard could pull 3 or 4 sleds in a train without straining. But ice is never perfectly predictable. Temperature swings were the killer. A warm day, anything above 20 degrees Fahrenheit, could soften the surface just enough to create ruts. The Lombard's tracks would bite in, the sleds would drag instead of glide, and the load resistance could double or triple. Operators had to throttle back, reduce speed, sometimes uncouple sleds and make multiple trips. Worse, a warm spell followed by a sudden freeze created layered ice with different densities and strengths. The top layer might hold, but the layer underneath could be weak, honeycombed with air pockets. When 20 tons of Lombard rolled over that kind of ice, you didn't get a warning. You got a crack like a rifle shot, and then the surface gave way. Accidents were documented in camp logs, company reports, and local newspaper accounts. A Lombard breaking through ice on a frozen lake was a catastrophe. The machine would plunge through, sometimes tipping forward as the front skis dropped into open water, dragging the boiler and engine down with them. If the engineer and firemen were lucky, they have time to jump clear before the machine went under. If they weren't, they went down with it. Recovery operations could take weeks, waiting for the ice to thicken again, then using block and tackle to winch the wreck back to the surface. Several Lombards were abandoned entirely, left at the bottom of lakes or rivers where the cost of recovery exceeded the machine's value. Cable and chain failures were another constant threat. The chains connecting the sled train were under immense tension. 10, 15, sometimes 20,000 pounds of pulling force transmitted through steel links. A cracked link, a worn pin, or a chain that had been overstressed in a previous season could fail without warning. When a chain snapped under load, it didn't just fall to the ground. It whipped. A count from a period described chains lashing back with enough force to shear through tree trunks or cut a man in half. The brakeman, riding on the rear sled, was in the most dangerous position. His job was to watch the chains, listen for the sound of stress, and signal the engineer to stop if anything looked wrong. But in a blizzard, with visibility down to a few feet, there was no time to signal. You heard the crack, and you jumped. Mechanical failures happened in the field, far from any shop. A broken track cleat could strand a machine in deep snow, its weight pressing it down into a drift until the remaining cleats lost purchase and the track spun uselessly. A ruptured steam line could vent all your boiler pressure in seconds, leaving you with a dead engine miles from camp. A seized bearing in the drive shaft could lock the entire powertrain, turning 20 tons of iron into an immovable obstacle blocking the trail. Crews carried spare parts, extra cleats, replacement pins, sections of chain, gasket material, valve springs, but some failures couldn't be fixed in the field. In those cases, the only option was to unhitch the sled train, abandon the Lombard where it sat, and send word back to camp for a heavier wrecking crew or, in some cases, a second Lombard to tow the first one out. The boiler itself was the most feared hazard. Steam at 150 psi, contained in a riveted steel vessel, represented stored energy equivalent to a small bomb. If the water level dropped too low, either from a leak, from excessive consumption, or from the firemen losing track during a long haul, the firebox could heat the crown sheet, the top of the firebox inside the boiler, until the metal softened and failed. When that happened, the boiler didn't just leak, it exploded. Superheated steam and boiling water erupted outward, scalding everything within a 30-foot radius and often killing the engineer and fireman instantly. Period records mention at least 3 documented boiler explosions involving Lombard haulers between 1905 and 1920, each resulting in multiple fatalities. Risk wasn't theoretical. It was baked into every shift, every mile, every decision. The men who operated these machines understood the dangers and accepted them because the alternative, going back to horses and hand labor, was economically unthinkable. But acceptance didn't mean recklessness. The best crews were cautious, methodical, and deeply attuned to the machine's behavior. They survived not by ignoring the risks, but by respecting them. The Lombard steam log, hauler, didn't just improve winter logging. It redefined what was possible economically and geographically for the timber industry across the northern United States. The productivity leap was staggering. Before the Lombard, a team of 8 horses working a full winter day could extract 20 to 30 tons of timber from the forest to the mill or rail yard. That assumed good weather, well-maintained ice roads, and no major breakdowns. A single Lombard, operating on the same route under the same conditions, could haul 200 to 300 tons per day, 10 times the output, with a crew of just 3 men instead of the 2 teamsters, and support crew needed for multiple horse teams. The economics were brutal and simple. One machine replaced 40 to 60 horses, eliminated the cost of feeding and housing those animals, and reduced labor costs by more than half. But the real transformation was in reach and reliability. Horses had limits. They couldn't work effectively in temperatures below zero, and extended cold exposure killed them outright. They couldn't handle steep grades with heavy loads. Anything over a 4 or 5% incline required doubling the team, which meant twice the animals, twice the handlers, and half the efficiency. And they were vulnerable to injury and disease in ways that machines weren't. A Lombard could work in 40 below, whether as long as a fireman kept the pressure up. It could climb 6 or 7% grades with a full load, grinding uphill at walking speed, but never stopping. And it didn't get sick, didn't need rest beyond refueling and water, and could operate 12 or 14 hours straight if the crew was willing to endure the cold. Geographically, the Lombard opened territory that had been economically inaccessible. Some of the best timber in Maine, New Hampshire, and Michigan grew in high country, on ridges and slopes where building roads was prohibitively expensive and maintaining ice roads with horses was nearly impossible. Lombards could work those routes because they created their own traction. They didn't need a smooth surface, just ground frozen solid enough to support the weight. Logging companies that had written off entire sections of forest land as too remote or too steep suddenly found them viable. The machine didn't just extract more wood from existing operations. It expanded the total area that could be profitably logged. The economic ripple effects extended far beyond the timber camps. Sawmills that had operated seasonally, shutting down in winter when the timber supply dried up, could now run year-round. That meant steady employment for mill workers, consistent output for lumber wholesalers, and predictable supply for construction companies building homes, factories, and infrastructure in the rapidly growing industrial cities of the Northeast. Railroads benefited too. Lombards hauled logs to rail sidings faster and in greater volume, which meant more freight tonnage and more revenue per mile of track. By 1910, Lombard steam log haulers were operating across the northern tier of the United States. Maine remained the heartland. Alvin Lombard Home State had the densest concentration of machines, with some camps running 3 or 4 haulers simultaneously. But the design had spread to New Hampshire's White Mountains, to the Upper Peninsula of Michigan, to the forests of northern Minnesota and Wisconsin, and even the Pacific Northwest, where a handful of operators experimented with Lombards in the Cascade Range. Each region adapted the machine to local conditions. Some used coal instead of wood for fuel. Others modified the track width or ski design for different snow types. But the core engineering remained Lombards. Comparisons to modern equipment are revealing. A typical diesel-powered forwarder used in contemporary logging operations can haul roughly 15 to 20 tons of logs per load, working on prepared trails or roads. The Lombard, operating a century earlier with steam power and no hydraulics, matched or exceeded that capacity on a per-trip basis. And because it could pull multiple sleds in a train, its total payload often surpassed what a single modern machine could handle. Where modern equipment has the advantages speed and fuel efficiency, a diesel forwarder can cover more ground per hour and uses less fuel per ton moved. But in extreme cold and deep snow on rough terrain, the Lombard's simplicity and mechanical robustness gave it an edge. There were no fuel lines to freeze, no batteries to die, no electronic sensors to fail. As long as you had wood to burn and water to boil, the machine ran. The transformation wasn't just about tonnage. It was about changing the fundamental relationship between human labor and natural resources. Before the Lombard, winter logging was a brutal, seasonal grind that consumed men and animals at a horrific rate. After the Lombard, it became a mechanized operation where skill and knowledge of the machine mattered more than raw physical strength. The job was still dangerous, still exhausting, but the nature of the work had shifted. You weren't fighting the forest with muscle and willpower. You were operating a tool, a powerful, temperamental, unforgiving tool that amplified your decisions and made the impossible routine. Nothing lasts forever, not even iron beasts built to conquer winter. The decline of the Lombard steam log hauler began in the 1920s, not because the machines failed, but because the world around them changed. Gasoline and diesel engines had matured. Tractors powered by internal combustion were lighter, faster, easier to operate, and didn't require firemen to keep a boiler running. They could start at the turn of a key instead of an hour-long ritual of fire building and pressure raising. And crucially, they could work year-round, not just in winter. A diesel tractor could haul logs on dry ground in summer, on mud in spring, on gravel roads whenever they existed. The Lombard, for all its power, was a specialist, magnificent in snow and ice, but useless in any other condition. Road construction accelerated the shift. State and federal governments began investing in rural road networks during the 1920s and 1930s, building gravel and dirt roads into logging country that had previously been accessible only by rail or ice road. Once you had a road, even a rough one, you didn't need tracks and skis. You needed wheels and an engine. Logging companies that had invested heavily in Lombards found themselves with machines that were increasingly obsolete, not because they couldn't do the job, but because the job itself had evolved. The economics tipped decisively when a single diesel tractor, costing half as much as a Lombard and requiring one operator instead of three, could do 90% of the work with far less maintenance. The last commercial Lombards operated into the 1930s, mostly in remote camps in northern Maine and the upper Midwest, where roads still hadn't penetrated and the old ice road system persisted. By then, they were relics, kept running by engineers who'd spent decades learning their quirks and crew chiefs too stubborn or too nostalgic to abandon them. Maintenance became increasingly difficult as Phoenix Manufacturing stopped producing parts and the original suppliers went out of business. Operators fabricated replacements in camp forges, scavenged parts from wrecked machines, and improvised solutions that would have horrified Alvin Lombard. Some haulers were converted to stationary power plants, their boilers and engines repurposed to run sawmills or generate electricity for remote camps. Others were simply abandoned where they'd last worked, left to rust in clearings or dragged into barn sheds and forgotten. Alvin Lombard himself lived to see the rise and fall of his creation. He continued inventing and tinkering until his death in 1937, holding over 30 patents for improvements to steam traction engines, log haulers, and tracked vehicle systems. He never became wealthy from a Lombard hauler. Most of the profits went to Phoenix Manufacturing and the regional dealers who sold and serviced machines. But he had the satisfaction of knowing he'd solved a problem everyone else had called impossible. He'd built a machine that worked, that saved lives by replacing animals and brutal manual labor, and that helped extract the timber that built America's industrial cities. Today, surviving Lombard steam log haulers are rare and precious. The Maine State Museum in Augusta displays a fully restored example, complete with sled train, and operates it occasionally for demonstrations. The Patton Lumbermen's Museum in Patton, Maine, houses another, alongside exhibits detailing the history of logging in the North Woods. A few privately owned haulers exist in collections across New England and the upper Midwest, some operational, most static displays. Estimates suggest fewer than a dozen complete machines survive out of the roughly 200 that were built between 1901 and 1917. The rest were scrapped for their steel during World War I and II, or simply decayed in place until they were unrecoverable. The Lombard's influence extended far beyond its own operational lifespan. Military engineers studying tracked vehicle design in the 1910s examined Lombard haulers and incorporated lessons about weight distribution, track tension, and steering mechanisms into early tank designs. The Holt Manufacturing Company, which later became Caterpillar Incorporated, developed its own track tractors using principles that paralleled Lombard work. While Holt and Caterpillar went in different directions, focusing on agricultural and construction applications rather than snow and ice, the fundamental insight was the same. Continuous tracks distributed weight and provided traction where wheels failed. The legacy isn't just mechanical. It's about the men who operated these machines under conditions that would shut down most modern operations. Engineers who sat on open platforms in 40 below cold, throttle in hand, reading the terrain and the machine's behavior with a precision born from experience. Firemen who kept steam pressure steady through blizzards and breakdowns, improvising repairs with whatever tools they had. Brakemen who rode the sled trains, watching chains under 20,000 pounds of tension, ready to jump if something snapped. These weren't mindless laborers. They were skilled technicians who understood physics, mechanics, and the unforgiving reality of work in extreme environments. What did they know that we've forgotten? They understood that complexity is a liability. When you're 50 miles from the nearest shop, they knew that a machine you could fix with a hammer a wrench, and a fire was worth more than a machine that required a computer diagnostic tool. They recognized that steam power, for all its inefficiency and danger, had one undeniable advantage. As long as you could burn fuel and boil water, it ran. No batteries, no spark plugs, no fuel injectors to freeze or clog. Just heat, pressure, and iron. The Lombard steam log hauler was never the best solution in absolute terms. It was loud, inefficient, dangerous, and temperamental, but it was the right solution for a specific problem at a specific time. Moving massive loads across frozen terrain, that would stop anything else. And in that narrow, brutal niche, it was perfect. If this story of engineering, grit, and the men who conquered winter with steam and steel moved you, hit that subscribe button. We're diving into more iron beasts that build America, machines that modern engineers study not because they were advanced, but because they work when nothing else could. Drop a comment and tell us which machine you want to see next. The age of steam may be over, but the lessons it taught are timeless. Stand in front of a Lombard steam log hauler today, in a museum, silent and cold, and you're looking at more than a historical artifact. You're looking at a monument to a kind of knowledge that's almost extinct. Modern engineers can calculate stress loads to 6 decimal places. They can simulate thermal expansion in computer models, optimize fuel efficiency with electronic engine management, and design machines that operate with minimal human intervention. All of that is progress, real and valuable. But somewhere in the transition from steam to diesel, from mechanical to electronic, from analog to digital, something was lost. Not technology. We gained that. What we lost was the ability to build machines that a competent mechanic could understand completely, repair with basic tools, and operate reliably in conditions where complexity itself becomes a failure point. The men who ran Lombard haulers in the main woods knew their machine in a way few modern operators know theirs. They could diagnose a failing valve by the sound of the steam leak. They could feel a loose track cleat through the vibration in the platform deck. They knew how much throttle they could give on a 6% grade before the tracks lost traction, and they knew it not from a manual or a training video, but from experience, from the feel of the lever, the rhythm of the engine, the tension in the chains behind them. That knowledge was hard-won, earned through mistakes in close calls and long shifts in brutal cold. But it was complete. An engineer who understood his Lombard could keep it running under almost any circumstances, because the machine was simple enough to be fully known. Compare that to a modern logging forwarder. Hydraulic systems with dozens of hoses, fittings, and seals. Electronic fuel injection, controlled by microprocessors. GPS-guided navigation, load sensors, automated transmission systems. All of it makes the machine faster, more efficient, more productive. But when something breaks in the field, a failed sensor, a corrupted control module, a hydraulic line that's leaking somewhere in a maze of components, the operator is helpless. You can't fix a computer with a pipe wrench. You can't improvise a replacement for a proprietary electronic part. You call the dealer, wait for a technician, and lose days of productivity. The Lombard, for all its dangers and limitations, gave its operators agency. If the machine broke, you fixed it. If you didn't know how, you learned. And because the system was mechanical, visible, tangible, governed by principles you could see and touch, learning was possible. The firebox heated water. The steam drove pistons. The pistons turned the shaft. The shaft drove the tracks. Every component was accessible. Every function was observable. There was no black box, no hidden process you had to trust without understanding. The machine kept no secrets from a man willing to learn. That's the wisdom we've forgotten. Simplicity is a feature, not a flaw. In stable environments, where support infrastructure exists and failures can be quickly addressed, complexity is manageable. But in extreme environments, whether that a frozen forest in 1910 or a remote work site today, simplicity becomes survival. The Lombard worked in places where nothing else could because it was robust, reparable, and fundamentally understandable. It didn't need a support network. It needed a competent crew. There's a parallel here to a broader trend in modern technology. We build systems that are incredibly capable, but also incredibly fragile. Systems that work flawlessly under ideal conditions, but collapse when conditions deviate from the expected parameters. A Lombard operator expected deviation, expected the unexpected. The machine was designed for a world where nothing went according to plan, where every day brought new challenges, and where the ability to adapt and improvise was a difference between success and disaster. Modern systems, by contrast, are often designed for a world that exists only in theory, a world of perfect data, stable conditions, and reliable support infrastructure. The Lombard's legacy, then, isn't just about tracked vehicles or steam power. It's about a philosophy of engineering. Build machines that people can understand, repair, and operate with the resources they have available. Don't optimize for theoretical perfection. Optimize for real-world resilience. Accept that complexity as costs, not just in money, but in knowledge, independence, in vulnerability to cascading failures. Sometimes the best tool isn't the most advanced. It's the one that still works when everything else has failed. The men who operated Lombard steam log haulers are gone now. The last veteran of the steam logging era passed away decades ago. The knowledge they carried, the feel of the throttle, the sound of a healthy boiler, the art of reading snow conditions and ice roads, died with them. What remains are the machines themselves, silent in museums, and the records they left behind. Camp logs, maintenance journals, photographs of crews standing beside their iron beasts, faces weathered by cold and work, expressions serious but not unhappy. They knew what they'd accomplished. They'd taken a machine that everyone said wouldn't work and made it indispensable. They'd mastered winter with steam, steel, and understanding of physics that no computer could replicate. That knowledge is worth remembering, not because we should abandon modern technology, but because the principles that made the Lombard work, simplicity, robustness, understandability, adaptability, are timeless. They apply as much to software systems as they do to steam engines, as much to organizational structures as they do to mechanical assemblies. The world changes. Technology advances. But the fundamental trade-offs between complexity and resilience, between optimization and robustness, between theoretical perfection and practical reliability, those remain constant. The Lombard steam log hauler conquered winter, but its real victory was proving that engineering isn't about building the most advanced machine. It's about building the right machine for the job, the one that works when it matters, that people can trust because they understand it, and that keeps running long after more sophisticated systems have failed. If you made it this far, you're the kind of person who understands why these machines matter. Hit that subscribe button and join us as we uncover more forgotten iron beasts and the hard-won wisdom they represent. Comment below with the toughest machine you've ever operated or worked on. We want to hear your stories. And remember, the past isn't just history. It's a library of solutions to problems we're still facing today. The question is whether we're willing to learn. Educational and entertainment disclaimer. The content on American Iron Beasts is produced for educational and entertainment purposes only. While every effort is made to present historically accurate information about machines, terminology, and industrial practices, this channel does not replace academic research or professional technical study. Historical descriptions, measurements, and interpretations may be simplified for storytelling purposes. Viewers are encouraged to consult primary sources, technical manuals, and academic references for deeper or specialized research.